Hey, Chem 240. This is Dr. Ricardo here. We are going to cover Chapter 12. This is the first video for Chapter 12. We may have two. We'll see. Okay, I'm going to try to keep this one to an hour. So Chapter 12 is on solids and modern materials. And most of the content that we're going to talk about in this video, and you're going to be responsible for the test, is the study of traditional materials. Okay, we're not going to put a big emphasis on the modern materials section. Okay, so the first thing that we want to talk about is defining different types of solids. Okay, so the types of solids are going to fall into three major groups. The first type are called molecular solids. Molecular solids consist of atoms or molecules that are held together by intermolecular forces, what we studied in the last example. Here are three examples. Okay, the first best example would be ice. So there are individual water molecules that are locked into a very particular open crystal structure that repeats over and over and over again and gives ice a very stable structure. Okay, so ice would be an example. The covalent bonds between the oxygen and the two hydrogens within each water molecule are incredibly strong and are not broken when ice is melted. When ice is melted, the only thing that's broken are the weaker intermolecular forces that exist between one water molecule and another water molecule. Okay, so maybe later on I'll show you a description of what the crystal structure for ice looks like. But again, the moiety, the individual units that are going to repeat over and over and over again, are individual water molecules. That's why it's called a molecular solid. Dry ice would be another example. The individual very strong bonds between the carbons and the oxygens and the carbon dioxides, okay, are held together, and what holds the ice together is the bonds between one carbon dioxide and another carbon dioxide. So again, dry ice has a very particular crystal structure where all of the molecules are arranged in a certain way to make up the dry ice. None of the molecules can move around. We learned that in the last chapter. And the third example would be an atomic solid, something as simple as neon, which you usually think of as neon gas. If you cooled it down, could get it to liquefy. Cool it down further, you could get it to form a solid. The individual neon atoms would form a very particular crystal structure that would repeat over and over again. Okay, so that's the first type, molecular solids. Sugar would be another example of that, a molecular solid. Metallic solids are different. Metallic solids are what we think of when you think of a piece of iron, right? There is a crystal structure that goes on inside a piece of iron, and we call the bonds between the individual metal ions that I have drawn down here, right, as being the structure for the metallic solid. So they have a crystal structure. Both of these have a very specific crystal structure. Okay, so let's read this. It consists of positive cores of atoms held together by a surrounding sea of electrons. So here's an example of something that you don't usually think of as a solid, but I could have a piece of sodium metal. Now, very different from sodium chloride. Okay, a piece of sodium metal would look like a metal. It would be shiny, just like aluminum. Okay, maybe even more shiny than aluminum. Okay, it's a very reactive material. Happens to also be soft. Okay, you take this solid sodium metal, and let's dive into what the atoms are doing underneath. So if this is a piece of metal, so think of the surface being up here, right? Here are the individual sodium cores. So those sodium cores are positive 1 because they consist of a sodium nucleus that has 11 protons and 10 electrons that it holds onto very strongly. The last electron in sodium, if you remember, is the only electron that's in the third orbital, right? This would be a 3s1 electron. Down here, the two shells before that, the 1s2, 2s2, 2p6, that whole arrangement is the core of the sodium ions. That is very tightly held together and stays together. But this last loosely held electron is free to move around the solid. That's what makes metallic solids very conductive. They have 1, 2, usually not more than 3 extra electrons in their outermost shell that are free to move around. So when you heat up sodium, what happens is those electrons bounce around and they move quickly and they transfer energy from one ion to another. So metals are very thermally conductive. Heat moves through them due to this movement of the sea of electrons. Okay, so these are all electrons that are zipping around. Important thing to remember is there are an equal number of these sodium cores, 6 of them, as there are electrons. So the whole metal has no charge. But this last one isn't isolated to one particular sodium atom. It more moves around the whole metallic solid. Metallic solids also conduct electricity very well. Well, if you think about this as a bar of sodium, and then all of a sudden you put a net positive charge on this side and a net negative charge on this side, put it between two DC wires, right, where this side is positive and that side is negative, then what's going to happen is these negative electrons are going to be drawn towards the positive. So electrons, these last free electrons, are the entity that carries the electricity through the charged material. So if this was a piece of wire, the electrons would tend to move this way. One would bounce this way, hit that one, bounce this way. So there would be a net motion in this direction. They'd have to be coming in from this side, from the negative side, and leaving towards the positive because opposites attract. So that's an example of a metal solid. I could do this with a piece of sodium metal like I did here, or I could do it with any element in the periodic table on this side, right? All of those metals on the left-hand side of the periodic table, the vast majority of these elements, how would they exist in their elemental form? As metallic solids. You could have a piece of chrome. It would have, usually it's chrome plus 3, it would have 3 free electrons moving around to constitute the sea of electrons. Manganese, iron, copper, cobalt, copper, nickel, all of these things, zinc, these are all good conductors of electricity because they have this property of the last few electrons being mobile. Okay? Don't want to over-explain it. Okay, so that's 2 types, right? We have molecular solid, then we had metallic solid. Well, what about ionic substances? They have very strong bonds. Well, they consist of cations and anions. There's no free electrons. The free electrons have already been transferred, and they're held together by electrical attraction because opposite charges attract. These are an ionic bonds, the way you learn them in Chem 1. So here's a 2-dimensional example of salt. Na plus 1 and Cl minus 1, right? They have both already, the sodium has already lost its electron to chlorine, and it exists in an arrangement of ions, okay? A crystal lattice of ions in which the number of sodiums and the number of chlorines are equal. So let's pick this. Anytime you see a positive sign, that's the sodium. Anytime you see the negative sign, that's the chlorine. So let's pick this sodium right in the middle of this array of 6. Forget this last group right here, okay? Well, what are its nearest neighbors? Well, it's positive. It's got a negative right on top of it, and a negative underneath it, a negative to the right, and a negative to the left. Those are its nearest neighbors. Its nearest neighbors in this flat representation, just cover these guys up for a second, okay? Its nearest in the flat representation are all opposites, okay? Well, if this is a perfect cube of 1, 2, 3, 4, 5, 6, 7, 8, 9 ions, this one down here, right? This is a unit 1, and this is unit 1. This one must be, by Pythagorean theorem, the square root of 2. Well, what's the square root of 2? 1.41. So this distance here to the next closest sodium ion is 1.41 as compared to the next chloride ion, which is only 1. So this guy would be 1, 1, and this one over here would be the square root of 2, which you know is 1.41. Well, this kind of packing, this kind of arrangement is critical because you want your nearest neighbor to be an opposite ion. Now, In reality, this isn't just two-dimensional. Let me erase that. Doesn't just exist as flat tiles. There's actually three dimensions. So there's another sheet of ions on top of it and another sheet of ions underneath it. Let's talk about the nearest neighbors to that middle sodium again. The next one up here, right on top of it, would be a chloride, right? Because that's its nearest neighbor. And the one on the other side, underneath it, would be a chloride as well. So it's 6 nearest neighbors. 1, 2, 3, 4. Top and bottom, which you can't see, those 6 ions are opposites. Well, if you did this chloride ion and took this side out, you'd get that same effect. Look at its 6 nearest neighbors at a distance of 1, right? This is going to be a sodium, a sodium, a sodium, and a sodium, plus a sodium on the top and plus a sodium on the bottom. So if I ask you to draw the next 6 on top of here, right, they would all be opposites, and that pattern would continue, right? And then on top of that would look identical to this row over here, and then on top of that would be identical to the second one that we just drew. So this pattern that you can see just repeats over and over and over again. So again, we have a two-dimensional representation. We're going to make it a three-dimensional representation in a bit. But again, ionic solids consist of individual ions held together by electrostatic attraction. Opposites attract. Okay, and the last, so these are very strong. So let's just review quickly. What do we have? Molecular solids, metallic solids, ionic solids, and covalent network solids. Covalent network solids are by far the strongest. They are one giant molecule. They consist of covalent bonds from one end of the molecule, pretty much, all the way through to the other end of the molecule. The greatest example is diamond. Diamond is a three-dimensional network of carbon atoms. We'll do an example later on. I'll show you the crystal structure of diamond. Okay, you can fit it into a unit that looks like a cube if you turn it the right way, and that cube can repeat over and over again. We can always fit them into a unit usually that looks like a cube or looks like some kind of regular shape. But the important thing is they consist of atoms held together by large networks of chains of covalent bonds. So diamond, okay? Graphite is also a different allotrope of carbon. Graphite looks like sheets of covalently bonded carbon atoms where there are very strong forces. They almost look like hexagons in individual sheets. And then there's another sheet on top of it and another sheet on top of it. The bonds between the sheets are weak. That's why you can write with a graphite pencil. Okay, you're not going to write with a diamond, okay, because diamonds are three-dimensional in their crystal structure. Graphite are more like sheets. And the third allotrope of carbon, okay, the third allotrope of carbon is asbestos. It is long chains of carbon atoms that are covalently bound together. This stuff is dangerous because these chains can be broken off, and they can be 50, 100, 200, 500 molecules long. That's tiny. Those asbestos particles that are all just carbon atoms, okay, are dangerous because we can easily breathe them in and get them into our lungs. Even though they're very inert, they don't really react with anything in our body, they cause cancer just because there's a foreign material inside our body that our body doesn't have. We breathe it into our lungs, and we don't know have any way to exhale to get rid of it, so it causes us lung disease. Okay, we're going to skip. Well, let me see if I can show you this overhead that I'm referring to from the chapter, okay, which would be 3 different versions of carbon, all of them who form network solids. Again, network solids are the strongest. Ionic bonds are the second strongest. Metallic are weaker than them, and the weakest are just molecular solids. Okay, so let me see if I find examples of the carbon. Okay. They don't have the asbestos, but they have the diamond and the graphite. So graphite is an easier one to see. So let me blow this up a little bit and I'll show you the graphite. So what did we say? Network solid, covalent bonds between all of the atoms inside the sheet, right? All right. Let me see, they don't show you, but these lengths in between the atoms within a sheet, look how close they are together. Much closer than the distance between one sheet and another sheet, okay? So inside the sheet, the atoms are much closer than 3.31 angstroms long. Remember, an angstrom is 10 to the minus 10th meters. So I would say these are probably around 2 or so angstroms long. Okay, so when you write with a graphite pencil, you're not breaking the bonds in this direction and ripping these guys apart. You're peeling off the first layer, then the second layer and the third layer and depositing them on the pencil, on the paper, and that's what you're writing with. So this is carbon in the graphite form. Okay, it can undergo under intense heat and pressure. You can transform carbide in the graphite form into this much stronger, much tighter, three-dimensional array of carbon atoms where every carbon, there's no hydrogens on here, these are all 100% carbon. It's just a network of tetrahedrons. Remember that from Chem 1? That's a tetrahedron up at the top. This bond angle would be 109 degrees. This guy heads down, look, into another tetrahedron, into another tetrahedron. And that crystal structure just repeats over and over and over again. And that's what forms diamond. The strongest substance on the earth, because you can basically take covalent bonds all the way through the whole solid and just keep going millions and millions of atoms until you can see the whole diamond on somebody's finger, on somebody's ring. Can't do that ordinarily, right? You can't just have covalent bonds from one side of a material to another. Like a piece of paper, that's not true. Okay, there's not carbon covalently bound from one to another. I'd never be able to rip the piece of paper. There are much weaker intermolecular forces between the molecules that are in the paper that are holding it together. Okay, so 2 examples of these network solids. Okay, let me go back to the page that I was going to work on next. I don't want to lose that. Good. Next page. Okay, try to go through this a little bit quickly because a lot of this stuff, these properties are kind of common sense. Let me see if I get all the columns on there. Okay, hopefully that's big enough that you can see. These are properties of different solids. So we have the types of solids that you're responsible from weakest to strongest, molecular, metallic, ionic, covalent network, right? This would be something like water. This would be something like diamond, NaCl, sodium, or iron. Okay, what about their melting point? Well, remember, melting point is a representation of how easy it is to break the intermolecular forces between the molecules. So the lowest ones, okay, are going to be the molecular solids. Ice is very easy to melt. Solid oxygen is very easy to melt. It's already melted a long time ago at much lower temperatures. Okay, then the metallic solids. So even though you think metals would be hard to melt because of their high molecular weight, relative to ionic substances and covalent network substances, they're easier to melt. It would be easier to melt sodium solid than it would be to melt sodium chloride, which is an ionic solid consisting of sodium ions and positive ions and chlorine negative ions. Okay, so from top to bottom, the ones with the highest melting point would be the covalent network solids, all the way to the lowest, which would be molecular. Good? All right, what about hardness? Well, hardness, again, is a representation of the strength of the material. Okay, so the hardest material would be something like diamond, right? Hardest material pretty much known to man. Okay, very hard. Hard to break the bonds between them because they're very strong covalent bonds. Okay, ionic substances tend to be hard, okay, but they're brittle. If you take a hammer and you smash them, you'll break them into individual smaller crystal structures. Okay, they're still going to break along certain fracture lines. You're going to break them into pieces that show the way the ions are arranged. But if you pound on them, okay, they're not going to bend like a piece of metal. They're going to break like glass into much smaller pieces. Okay, don't think of glass so much because glass is a special case. Think of break like if you hit a big chunk of ice, it would break into smaller blocks of ice. Okay. All right. Or a better chunk of salt, right? A big chunk of salt, hit it with a hammer, it's going to break into smaller blocks of salt. Okay. Metallic have variable hardness, and they're said to have this property called malleability. If you hit it with a mallet, you can break it. Okay. So you can take a piece of aluminum or iron or steel, which is more than 90% iron, you can hit it with a hammer, okay? And instead of it breaking into a million pieces, it'll bend and take the shape of whatever you hit. So these materials, metals, can be machined and banged out, okay, and hammered to give us, and that's how in the old days we made our fenders for automobiles. Now they're all made out of plastic. Okay, your car is basically plastic. Okay, in the old days they were made out of metal that had to be banged out. Okay, and the weakest and softest and most brittle, easiest to break would be something like ice, which is a molecular solid. So hardness goes from the bottom to the top, melting point, highest to the lowest. Okay, how about conductivity? Okay, in order for something to be conductive, you need to have an entity, a charged particle that's easy to move around. The only one of these groups that has free electrons, those outer shell electrons that are living in the sea of electrons, is the metallic solid. So metallic solids are very conducting of both heat and electricity. These go together. If something allows heat to move through it, it also allows electricity to move through it. Very rare that something does one without the other. Okay? That would have to be like a semiconductor or something like that. Most traditional materials, as the conductivity for heat goes up, so does the electrical conductivity. Okay? So, non-conducting, because there's no free ions, okay? Or no free particles to move around, no free electrons to move around. So I would not expect ice or dry ice or sugar to conduct electricity, a solid piece of sugar. Metallic substances, metallic solids, are very conducting because of those free electrons. Ionic solids, even though they're made up of ions, those ions can't move around when it's a solid. So they're non-conducting as a solid. If you melt them, right, and you had liquid sodium chloride, very different than salt water. You're not dissolving salt in water, you're liquefying salt. So if you liquefied salt, that would be conducting because the liquid, the individual ions, the sodiums and the chlorides, could move around past one another. And if you put them in a box where one side of the box was positive and the other side was negative, there would be a net movement of the negatives towards the positive side and the positives toward the negative side. That can't happen if you put a chunk of sodium chloride solid because the individual ions aren't mobile. And the last thing, the least conductive material, would be something that would be a network solid like a diamond. Okay, let's talk about crystal structure. Okay, so crystal structure is when a solid has a crystal solid, it has a well-defined order structure of the atoms in 3 dimensions. Here's some examples, a little hard to see. Let me see if I can put the light on, maybe that'll help. Nope, that makes it worse. Okay, I have my 3 examples are NaCl solid, this just says carbon diamond, and H2O solid. So you would have guessed that. These things all are, I could show you a 3-dimensional array in which the molecules or atoms or ions are arranged, and that pattern repeats over and over and over again. Okay? So water in the frozen state has a very defined pattern. So when you're looking at a big chunk of ice, billions and billions and billions of times, that individual pattern of about 12 12 to 15 water molecules, repeats over and over and over again until you get a whole giant piece of ice that you can hold on to in your hand. So that's what it means. Way down at the ions, molecules, or atoms, there is a repeatable pattern, a crystal structure. Okay? So crystal structure, crystal solid. Last term is sometimes we use the word crystal lattice. So crystal lattice is the geometric arrangement of atoms called the lattice points in space. Okay? Once in a while, you can get this weird state of solid, which is called an amorphous solid. An amorphous solid is unusual. An amorphous solid was in the liquid state, and it was frozen so quickly, it was flash frozen so quickly that the individual atoms or ions or molecules didn't have time to get in their lowest energy state, where the interactions between them are the best, are the lowest energy, right? That would be the crystal structure. They just froze any old way. So amorphous solids, and the best example of that would be glass, is something that was frozen quickly before the individual units had a chance to get into their crystal state. So that's why glass has properties very different than quartz. Even though they're both made up of silica dioxide, quartz took millions of years to cool down, and every silica dioxide, every SO2 entity got into exactly the lowest energy position in the crystal structure so that all of the interactions were minimized, right? What does that mean? All of the positives and negatives were in such a way that they interacted in the best fashion. Positives love negative, negatives love positive. In glass, you heat up sand. Okay, so Vineyard, New Jersey is a famous place for making glass because the quality of the quartz sand is so good. Well, what do? They melt the quartz glass, and then they flash freeze it just by taking it out and letting it cool down in the matter of an hour. Well, there's an hour is not a million years. So those individual silicon dioxide ions don't have time to crystallize. So what do? They just kind of arrange themselves in any old, more random order, and that's why it's amorphous. That's why when glass breaks, it just takes these circular patterns and all this weird stuff. That wouldn't be the way quartz would break. Quartz would break amongst very regular patterns and break off in tiny chunks that look like the big piece of quartz, because the overall arrangement of the way the atoms are arranged down at the molecular level kind of grows into the outward crystal that you see. So the reason why kind of quartz looks like the George Washington, or sort of the Washington Monument, right, which is something like this. All right, whenever you see crystals of quartz, they kind of look like this, and they're growing out, and they are all like that. That's because that's the way the atoms and ions are arranging themselves down, way down at the molecular level. So if you're arranging yourself in that pattern that looks like this, when you grow and you get millions of guys together, the outward pattern still looks like that. It's pretty amazing. Okay? So outward crystal structure, right? So for instance, when you see a diamond on someone's hand and you see the way it's cut, right? Well, those cuts are representative of the way that the carbon atoms are arranged, which is pretty neat. Okay, so let's read through this. An amorphous solid has a disordered structure. It lacks a well-defined arrangement of basic units, which are atoms, molecules, or ions, found in the crystal. And the key to making an amorphous solid rather than a crystal solid is melt it and then freeze it fast, okay, before the ions have time. Well, let's talk about specific unit cells, specific crystal lattices that you're going to be responsible for. Now, there's a whole group of them, okay? And I can show you them in the book. And when we go through them in lecture on the PowerPoint slides, I'm going to show you all of these different ways that the entities, remember, either atoms, ions, or molecules can be arranged. But overwhelmingly, the only one I want you to know is an arrangement called a cubic arrangement. So we have cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, or triclinic. Okay, so those are all the different kinds that we have, but again, you're only going to be responsible for cubic crystal structure. So this, down in pencil, a little hard to read, is the crystal system that you're talking about. Okay, there are 3 different cubic crystal structures. There is a simple cube, a body-centered cube, and a face-centered cube. Okay? In all 3 cases, the entities in the corners are the same. So you make a box in your head, and you know when you make a box, right, it's going to have 8 corners because the box is 3-dimensional. So I'll draw that for you in a second. In a simple cube, that's it. There's either an atom, ion, or molecule at each of those 8 corners and nothing else in between. And that pattern just repeats over and over and over again. Well, chemistry would be very simple if everything followed that pattern, but that's not the case. In fact, simple cubes, okay, aren't even that common in chemistry, okay? And I'll show you an example in a second. More common than that are the next 2, especially the third one. That's the one we're going to focus on. The next one is easy to see. A body-centered cubic structure has atoms, which we'll call lattice points. Now remember, lattice points can be atoms if it's an element, molecules if it's a molecular solid, or ions if an ionic solid, right? So atoms, molecules, or ions in the corners, and also another one right smack in the middle. So picture 1 atom at each of the 8 corners and 1 atom right smack in the middle. That makes sense, body-centered. In the body of the cube, right in the center, there's an atom, okay? Or a crystal, there's a point, something there. Good? Last one. A face-centered, which is actually the most common, has atoms at each of the 8 corners and also an atom right in the middle of each of the 6 faces. If you think of a cube, there is a top, a bottom, a front, a back, and a left and a right face. In each of those 6 faces, you would also stick an atom. So this one is much, much closer together than this one, and this one is much, much closer together than that. So if I was going to make these 3 different crystal structures out of the same element, okay, so then they would have the same size and mass, which one would be the densest? The face-centered, which would be the medium density, the body-centered, and which one would be the least dense? The simple, because it's got the most space between it. Holding everything else constant, that would be true. Okay? Now, face-centered cubic structures are going to have a repeating pattern that's called an ABC pattern. Okay? And we're going to see that in a little bit. Let me show you from your textbook an example of these 3, and then we'll do a practice question counting up all of the different lattice points in a sample of copper once I tell you what's going on in copper. Okay? All right, so here's 3 examples. I'll blow them up a little bit. Okay, top one, called a primitive cube or a simple cube, okay? Remember, everything's in a cubic crystal structure, everything's got to fit into a cube. That means the sides are all the same. Every one of these lengths is identical. So many substances that we find in nature have this pattern. Pretty neat that they repeat in a pattern where all of the sides are the same. Okay? Well, if I put an atom in each corner, right? There's one, there's one, there's one, there's one. So there's 4 on the top plus the 4 on the bottom. You can see 3, and then the one in the back you can't see so well. So why are they chopped like this? Well, because if they live in the corner, right? Really, this particular cube only owns 1/8 of that atom, right? only owns 1/8 of that atom. The other 7/8 exist in the other cubes that are around it. So let me show you where the other 7 cubes are. If this is our one over here, there's one right next to it down on the bottom shelf. There's one over here diagonally, right? And there's one in the back, right? So we'd have one here, right across, right? And one here. Let's do this one here. Okay, I'll make a little cross. Let me see if I do this. So we'd have one here on the bottom, one here, diagonal to this one right along this backside. So that would be one, this one, 2, 3, 4, plus the 4 in the sheet on the top, right? So here's the first one in our cube, then one would be in the second one next to it, the third one diagonal to it, the fourth one in this back spot, plus the 4 on the top, the one right on top of this one, the one on top of that guy, on the top on top of that guy, and on the top on top of that guy. So each one of these atoms is in the same situation. It only counts for 1/8 being inside the cubes because the other 7/8 are in the 7 other cubes that surround it. That's important. You have to memorize that. Okay? If you live in a corner, your crystal lattice that you're talking about only gets to count 1/8 of an atom. Well, let's talk about this. In this case, you've got 8 corners, right? So you've got 8 things, but they only count, I only have ownership of 1/8. But what's 8 times 1/8? 8 times 1/8 is a big fat 1. So in this case, there would be 1 atom in the unit cell, right? Because you've got 8 corners multiplied by 1/8. Where does the 1/8 come from? That's how much you own of that atom. The other 7/8 are owned by the other 7 atoms, 7 cubic cells that surround it. Good? All right, next one. Here's the body-centered cube. Well, we still have our 8 times 1/8 going on, right? So that would come over here as 8 times 1/8 equals 1. So we've got 1 atom so far in the cell, right? But we've got another atom that's right smack in the middle of this cubic cell. It doesn't touch any of the faces, it doesn't touch any of the edges, and it doesn't touch any of the corners. So there's 1 of them, and you get to count it as a whole. So 1 times 1 equals 1. So if I asked you, how many total atoms in a body-centered cube? The answer is 2. So this is twice as dense as this if they were the same size. Okay? If these walls, edges were the same size, I'd be able to put 2 atoms into this structure and only 1 atom into that structure. Okay? Let's see even more dense. Okay? Even more typical in chemistry. The most important of the 3. Hardest to understand, but most important, you see this a lot in nature, is the face-centered cubic metal. Okay? This is an example of copper that I'm going to show you in a second. Okay? So in copper, we have a copper atom. All of the atoms are identical. The only thing in copper are copper atoms. Okay? So we have, always you have to put the lattice points in the corner, right? They all have that in common. Lattice points in the corner, lattice points in the corner, and lattice points in the corner. So we have our 8 times 1/8 like we always have, right? There are 8 corners, and we own 1/8 of each corner. So I get 8 times 1/8 gives me a big fat 1. Good? But now I also have atoms in the faces. Now a face is like a tennis ball cut in half. Half of it is inside this unit cell, and the other half is in the one next to it, right? So does everybody agree, if I live in a face, I have to get counted for 1/2, because half of me is in this unit cell and half is somewhere else. So the only other thing I have to multiply by is how many faces are there? Well, there is the top, the bottom, the front, the back, the left, and the right. So there are 6. What's 1/2 times 6? That's equal to 3. So 3 plus 1 is 4. So look at that. If these walls or these edges were exactly the same length, the height, the width, and the length always has to be the same in a cubic structure. But if these lengths were the same as these lengths and these lengths, who's winning? Well, winning is highest density, I guess, right? Well, I don't know if it's a winning kind of thing, but I was able to fit 4 atoms in this cubic cell. I was only able to fit 2 in this one. I was only able to fit 1 in this one. So my guess is if you can jam the same entities in there, this one would be 4 times as dense as this one. Because what is density? Packing the atoms, molecules, or ions together tightly. Good? Now let me erase that. So you do need to remember that. If you are face-centered, you're going to be able to put 4 things in it, right? Why? 3 in the faces and 1 in the corners. If you're body-centered, it's going to be 2, 1 in the corners always, and 1 in the center. And if you are a simple cube, also called a primitive cube, okay? a little condescending name, okay? But a primitive cube would be just in the corners. So this one is 1, this one is 2, this one is 3. Okay. All right. So let's look at actual copper. If I asked you this on a test or in a homework, I don't even have to show you the crystal structure. I can describe it. Okay. So here's the question. Determine the number of atoms per unit cell for copper when copper has the following properties. How many copper atoms are in the unit cell of copper? Copper, solid, is a face-centered cubic chloride of copper atoms. And since it's a pure element, that's all there is. There's nothing else in there. There's no counter-ion. There's not another thing in there. It's just a face-centered cubic unit cell. And we just learned that if you're face-centered, you've got 6 faces times 1/2 gives you 3 atoms. And you always, in a cubic system, you always put the same atoms that you're describing in the corners. And you'll always have 8 corners. Most of the time, all 8 corners will be occupied by the same entity, right? Since we're dealing with an element, it's got to be the same entity because we only have one entity, right? We only have one thing. We only have copper. So 8 corners times 8 gives you 1. 3 plus 1 gives you 4. Okay? That 4 could be called the coordination number. It's the number of nearest neighbor atoms to any atom of interest. So if we go back, right, take this guy right here. He's got 4 nearest neighbors. There they are. 1, 2, 3, 4. You could do that for anyone. This guy. 1, 2, 3, 4. Even this guy over here, if you built the pattern out further, you would see his 4 nearest neighbors would be this one, this one, this one, and the one that you can't see up here. Okay. Okay. How do the atoms pack together to give you these structures? So there's 2 ways to pack them together. And this reminds me of if we got eggs, right? So I might run downstairs, pause the video for a second, run downstairs and get you some eggs, and you can realize what I'm talking about. So let me describe it first. So for molecular solids, they tend to be close packed materials. So simple molecular solids have non-directional forces between the molecules or atoms. And the maximum attraction is obtained when each atom is surrounded by the largest possible number of atoms. So there's 2 ways to have this close packing. One is an AB, AB, AB arrangement. In an AB, AB, AB arrangement, you would wind up with a hexagonal close packed structure, HCP. It's a crystal structure composed of close packed atoms or other units with an AB, AB, AB stacking. The structure has a hexagonal unit cell. Well, this is common, but not as common as this one. This is the one I want you to remember. The ABC packing is what we just looked at. It is a cubic close packed structure, okay? You are going to get a face-centered cubic unit cell when you have A, B, C packing. So let's read this. It's cubic close packing, CCP, is a crystal structure composed of close packed atoms or other units, like ions or molecules, with the stacking ABC. CCP close packing equals face-centered cubic chloride. This is an important note to memorize, right? If you pack them, put the first layer down, put the second layer in the holes between them, put the third layer in a new set of holes that developed after you made the first and second set, and then repeat the pattern. Here, you put the first set down, like eggs. Then you put the second set in the spaces between the eggs. Then you put the third set exactly on top of the first set. The second set exactly on top of the second set. So that would be a hexagonal close structure. Put a layer down, put a slightly different layer down in the holes, then repeat. Here, you need to go through 3 sets before repeating. Okay? I'm going to show you that in the book for a second. I will let the video run because it'll only take me a minute to run down to my refrigerator to get eggs so you can see what I'm talking about. Okay? Actually, I might. Okay, guys, so I went down to my refrigerator and I have 11 eggs here, okay? But I don't need that many to show you. But you can see, once you put down the first layer of eggs, there's definitely a natural spot. Like sometimes at our house, we have more than a dozen eggs. So what do? We take the older ones, we pull them out, put the newer ones at the bottom, and then we put the older ones on top because we want to eat the older eggs. But man, is that a natural spot. So once the first layer goes down, inside that hole, we put the next layer. Okay, so if I had a bigger amount of eggs, there would be more spaces. I would fill up the next set of holes, which would be here, and the next set of holes, which would be here. So both the hexagonal close packing and the cubic close packing, the first layer is going to do the same thing. The question is, when you get to the third layer, you're going to have 2 choices. That I can't show you. You can either put the next egg back identical to the first one. That would be if I put this next one and it went right here, right on top of the first layer, right? And then his partner would be next to that. That would be AB, AB, because the third layer is repeating the pattern from the first. If I do ABC packing, the third layer is going to go into a unique new space that's different, not on top of the first one, not exactly the same as the third one. So that space might be over here. This might open up where that's a unique third one. And then when I go through 3, then I repeat the pattern. That kind of packing will give you a cubic close packing structure. That's number 1. And number 2, it's a specific type that we're really going to focus on, and that is the face-centered packing, okay, or face-centered arrangement of the ions, atoms, or molecules, okay? All right, one more thing I'll show you from the book. This is on page 481 of your textbook, okay? And it just shows you, I could blow it up a little bit. Okay, here's the first layer. So this is going to be the hexagonal, which is going to be AB, AB. There's the first layer. I put that second layer just like the eggs. Then I put the third one directly on top of where the first ones are. What does it look like from the side view? It looks like A, and B is different. Then the third layer looks like A again, and that sandwich just repeats over and over and over again until I get a material that I could put my hands on, right? This is way down at the molecular or atomic level, okay? Here's our cubic close packing. The first layer starts out exactly the same. No difference between here and here. The second one, exactly the same. Doesn't get unique until the third layer goes on. So I'm looking down, right? These were all looking down here. The third layer goes into a unique new space, not exactly where the first one is, not where the second one is, but a new layer. What does that look like from the side? A, B, C. Then the pattern would repeat. What would go on top of here would be another set of A's, then another set of B's, then another set of C's. So it would be gray, blue, yellow in the next level. And that pattern would repeat this way, and it would also repeat down. Here, it would be gray, blue, gray this way. What's the next one underneath here? It would be blue. Got it? Good. Okay. Two more examples that I want to do. So what we're going to do is I'm going to ask you, this would be like a test question. Let me make it a little bit smaller. Okay, I can fit both of these views on here. Okay. And this is cesium chloride. So my question for you about cesium chloride is, if cesium chloride was packed like this, how would we describe its packing, and what would be the empirical formula of cesium chloride? How many cesiums would be in a repeating pattern with how many chloride? Now, ignore the fact that you secretly know the answer, right? That this is going to form a 1-to-1 salt because cesium's +1 and chloride is -1. Let me prove to you that in the pattern of in the arrangement of the way that the ions are packed, so this is an ionic solid. So how would I describe this to the world? I would describe this as cesium chloride is a simple cubic chloride, okay, with a cesium in the center of the unit cell. One more time, it is a simple cubic chloride with cesium in the center of the unit cell. I don't call this a body-centered cube because it doesn't have a chlorine in the middle. It has a different ion in the middle, okay? So that's the first thing, right? This would be a simple chloride with cesium in the center. And cesium is bigger and just sticks beautifully right in the center. So here's one way to look at it. Here's another way to look at it, right? Now what would happen with this? This pattern would just repeat over and over and over again a gazillion times until I got a white crystal that I could show you that would be cesium chloride, okay? All right, so here's the chlorides at each of the 8 corners, right? Here's the cesium right smack in the middle. Okay, let's get the stoichiometry of it. Let's look at the chlorides. We know that chlorides are in the corners. There's 8 corners. A corner always counts for 1/8 because 1/8 is in the box, 7/8 are on the outside. So 8 times 1/8 equals 1. What about the cesium? Well, super simple. That cesium is not shared with any other unit cells. It's right smack in the middle. Even in this view, doesn't touch the walls. It's not cut off. That means the whole thing, the whole cesium, is owned by this unit cell. So that's simple. 1 times 1 equals 1. Well, if you have a unit cell that has 1 chloride and 1 cesium, that's 1-to-1 stoichiometry. The empirical formula would be just CsCl. And you secretly know that makes sense because cesium's position on the periodic table means it's almost always +1 and chloride is -1. Let me see if I show you that. Okay, and then we're going to do another example. Let's do sodium chloride, which is even more interesting. Okay, so these are totally legitimate homework and test questions where I ask you to figure out what the stoichiometry, or better than stoichiometry, is what is the empirical formula of the salt or the solid or whatever it is that we're talking about based on me describing the crystal structure like this. Okay, so I did want to show you, let me see if I could show you one thing. Not important. Let's do this example. Okay. All right, so here's good old common table salt, sodium chloride. Okay, now secretly from Chem 1, you already know that sodium chloride is NaCl, because sodium is +1 and chloride is, again, -1. So first, how would I describe this to you? Now, this picture on the right is a little complicated because there's more than one unit cell. There's like 1.5 unit cells. So you either have to ignore this little piece on the left to think of 1 unit cell, or equally ignore this one on the right to get a pattern that looks like a cube. Okay, so I think it's a little easier to ignore this one. Okay, because if I ignore that one, right, I'm going to get the colors right with here. So sodium here, let's get this right. The chlorides are in the corners if I do it that way, right? So I want to do that. Okay. So that's what we have here. The bigger ones, the chlorides are in the corners. So you always describe it by the thing that's in the corners. Okay, so chlorides are in the corners. It's not a simple cube because chlorides are not only in the corners, right? Chlorides are the blue ones. Chlorides are also in the faces. Look at that. That's a tennis ball cut in half. So there's a chloride in that face, that face, that face, the one on this side, the one on the bottom, and the one in the back that you can't see. From this picture, it's this one, this one, this one, this one, this one, and that one. Remember, I've got to ignore those guys. Actually, let me do it this way. Ignore those, right? Who are the faces? The faces, that's, make sure I do it right. No, I gotta do it this way. Oh, you see, you have to cut this guy up, okay, because you want the chlorides to be in the corners. So the faces would be, this is a front face, back face, top, bottom, left, and right. 6 times 1/2 will give you 3. That's the faces. Okay. All right. So how else would I describe it? So again, going back to the beginning, this sodium chloride is a face-centered cubic chloride with, ready? Now I got to say the rest. Where are the sodiums? The sodiums are in this new space called an edge. Look at that. That guy is not a face. It's not a corner. It's called an edge. Just like the guitar player for U2, okay? His name is an old guy now, but he's a really good guitar player, even though you guys probably hate U2. His name is The Edge. He's a lot cooler than Bono. He doesn't, go shooting off his mouth all the time. He's a very quiet guy. And he always, he must be bald because he always has like a knit cap on, okay? He's a good guitar player. So there he is, The Edge, okay, or Edge, okay? So what's going on with the edge? Well, we got sodiums in the edges, and there's one more sodium that you can't see in this picture, but you can see in this picture, so we got to ignore that side. Who's in the absolute middle of the whole thing? One of the gray ones is sodium. Well, remember, if you're in the absolute center, the absolute minimum, you're not shared with anyone. So there's one guy, one sodium in each cubic cell right in the middle. Okay, last thing. What do edges count for? There's an edge. There's an edge. There's an edge, 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 and there's an edge. Okay, so how many edges are there and what should they count for? Okay, well, think about it. An edge should count for 1/4 in the cell that you're interested in. Okay, because unlike a corner that's shared 8 times, an edge is only going to be shared 4 times. It's going to be shared with the box right next to it in front, the one underneath that box, and the one underneath this box, right? Only 4, not like a corner which has 8 partners. So all you have to do for the edges is count up how many edges there are in a cube and multiply them by 1/4. Well, the answer to how many edges are in a cube is 12. Whenever you draw it, you'll draw it out of 12 lines. Ready? 1, 2, 3, 4 in the front box. 4 in the back, 1, 2, 1 you can't see, and the one in the back, that's 8. Then the 4 connectors, 9, 10, 11, and 12, the one that's back there. So there's 12 edges times 1/4. That's the way you do edges, okay? All right, here's the answer. if I said to you or showed you this picture for sodium chloride, and I said, what is the empirical formula of sodium chloride? Here's how you would get the answer. Okay? What's going on for the chlorines? We've got our famous 8 times 1/8 to give us 1. And then in the faces, 6 times 1/2 to give us 3. So in each unit cell, sodium chloride is very packed. There are 4 chloride ions. Ready? Where are they? The faces and the corners. The faces and the corners. So I would describe this as a face-centered cubic chloride with sodiums in the center and the edges. Okay, so if sodium is in the center and edges, center counts for 1 times 1 to give you 1, and edges, there are 12 edges times 1/4 to give you 3, right? 12 times 1/4 gives you 3. 1 plus 3 equals 4. Well, if I have a ratio of 4 to 4, empirical formula, I always simplify because the ions are just packed together and it's in a repeating pattern. So I wouldn't write Na4Cl4. For ionic compounds, I always simplify them into their empirical formula. 4 to 4 is the same as 1 to 1. And you knew that based on the charges. Okay? All right, I am going to take a break. That covers everything from the notes for the solids chapter. When we go through the PowerPoints, we'll have a small discussion on the modern materials, but the meat of the questions about solids will be about typical solids that we just talked about. Okay? And last thing, those are the only kinds of sort of entities that you can have, right, in any system. Let me get a piece of paper for you for a second. Right? You're going to be responsible for always cubic systems. So there's the front face of a cube, and there's the 4 lines that take it to the back, and then there's the 4 along there. So to put my little cube together, didn't I have to use 12 lines? Yes, there's 12 lines in this picture. Each one of those lines is an edge. So we know edges always count, right? There's always 8 of them. Ooh, excuse me. There's always 12 of them, and they count for 1/4, because 1/4 of every edge would be inside this particular cube. Okay? All right, what about if you're in a corner? Okay, well, if you're in a corner, then we said, I won't repeat that, we said there's 8 corners, and you're 1/8 ownership inside the box of interest, so you'll always get 1. Okay, what about if you're in a face, right, where are the faces? There would be a face right here, a face right here, so any atoms that are located in faces, and the one I can't really draw in the front here because it'll obstruct everything, okay? So how many faces are there? There's always 6 faces in any cube, and if you live in a face, you count for 1/2, so that's your math. Okay? And the last thing you can do is be in the absolute center of the box. Okay? So the center of the box is different than this C. That's C for corner. In the center of the box, there's only one thing usually in the center. Okay? Usually, if you have more things in there, like if there's 2 of them that are not shared, you just count up how many 2. But if you're in the center, you always count for 1. There's no fractions. Okay? So you get 1 times 1. Okay? Not going to add those up. But those are the only kind of entities. Faces, corners, edges, and things that are totally centered inside the box, not shared at all. They'll always be multiplied by 1. Edges will always be multiplied by 1/4. The corners will always be multiplied by 1/8. And faces will always be multiplied by 1/2. There's no other kind of places you can be. Think about it. You could be in a face, an edge, a corner, or inside the box. That's it. Okay, with that, that's 104 minutes. That's enough for one day. We will see you guys in chapter 13.